You know that feeling? Summer hits, you walk outside, and it's just like a wall of heat.
Yeah. Intense.
Now, imagine doing heavy physical work in that all day, like on a construction site. It's more than just uncomfortable. It's actually really dangerous.
Absolutely. The statistics are quite stark. You mentioned, what was it, over 61,000 heat-related deaths in Europe just in 2022.
Exactly. It's a serious issue. So today we're diving into something that could be a real game changer: active clothing. Basically, think workwear with its own built-in personal cooling system.
And it's tackling a problem that's only getting worse, right? With global temperatures rising, outdoor workers are facing much higher risks.
Definitely. Finding ways to cool them effectively without, getting in the way of their job is crucial.
It's a real challenge. How do you add cooling without adding bulk or restricting movement?
Well, that's what makes this research so interesting. Our source for this is an article from Applied Sciences published in 2024. It's called Integration of Active Clothing with a Personal Cooling System Within the NGIoT Architecture for the Improved Comfort of Construction Workers.
Bit of a mouthful, but the core idea is powerful.
Right. We're talking about potentially shifting how we approach workplace safety, how we think about workwear itself. This isn't just like a fan blowing on you.
No, it's much more integrated, and it ties into that bigger trend, doesn't it? Construction 4.0,
right.
Bringing smart tech onto the site.
Exactly. Using IoT, the Internet of Things, to directly help workers.
Mm-hmm.
So our mission here is to unpack this. How does this cooling clothing work? Is it effective? How does it fit into this idea of a smarter, safer work environment? Think of this as your shortcut to understanding a potentially groundbreaking solution.
So starting with the problem itself, heat stress. We know it's dangerous, especially for construction workers. They've got the outdoor exposure, the physical exertion.
It's a perfect storm, really. And standard protective gear can sometimes even trap heat, making things worse.
Precisely. So finding a cooling solution that works with the existing safety requirements is key.
And the tech they focused on is thermoelectric cooling. The Peltier effect, right?
That's the one. Basically solid-state cooling. You run electricity through these specific modules. TEMS, they call them.
TEMS.
Right. And one side gets cold, the other gets hot. New compressors, no refrigerants like your fridge or AC.
Which sounds simpler, maybe more robust.
Potentially, yeah. Fewer moving parts generally means better reliability, smaller size, lighter weight. Plus, they run on low voltage.
That's a big plus for safety, isn't it? Especially when you're talking about something warm close to the body. And easy to power with a power bank.
Exactly. And the research really highlights the development of flexible TEMS. That's quite important.
Flexible, so they're not like rigid plates sewn into your clothes.
No, they can actually bend and conform more easily, which is crucial for comfort and, actually being able to move properly on a job site.
Makes sense. You can't have workers feeling like they're wearing armor.
And this approach aligns well with the whole Construction 4.0 idea, an electronic solution for a physical problem.
Now, this isn't the only way people have tried personal cooling, is it? There are other methods out there.
True. There are systems using circulating chilled liquids or vests with phase change materials, things that absorb heat as they melt.
How does this TEM approach compare?
Well, the research suggests these TEM systems can offer similar, maybe even better cooling performance, and potentially with less weight and longer run times. They mention the coefficient of performance, the COP.
COP, okay, like efficiency.
Yeah, essentially how well it converts electricity into cooling. A higher COP means it's more efficient, potentially leading to longer battery life from the same power bank.
All right, let's get down to the specifics of what these researchers actually built. They made a prototype, right? A high visibility vest.
Yes, designed to be worn over standard protective clothing, which is critical for site safety.
So what's inside it? What are the key parts?
Okay, so you've got the flexible TEMS, 6 of them in this prototype. Then, importantly, heat sinks on the hot side of those TEMS.
To get rid of the heat generated by the cooling process.
Exactly. And they did something quite clever there. Used a super absorbent fabric on the heat sinks to add evaporative cooling.
Ah, using evaporation to boost the heat removal? Smart.
Definitely helps efficiency.
Mm-hmm.
Then there's a dedicated electronic controller, a skin temperature sensor.
To know how hot the wearer actually is.
Right. A standard 5V power bank for power and a pocket for the controller. Of course, the vest itself has reflective strips, adjustable straps, all the usual high-vis features.
Okay, the controller sounds like the brain here. What's its job?
Its main role is to manage the power going to the TEMS. It regulates it based on the temperature readings to provide controlled cooling.
So it's not just on or off?
No, it's smarter than that. It has components like DC-DC converters for voltage, a microcontroller, sensors for current and voltage, a little user interface.
Buttons, maybe an LED.
Yeah, buttons and a small screen. Plus, a micro SD card for logging data, and interestingly, a UWB radio module.
UWB, ultra-wideband. That sounds like it's for communication.
Precisely. This isn't just a standalone vest. It's designed to be part of a bigger system.
An IoT system on the construction site.
That's the idea. The UWB radio talks to these things called gateway edge nodes, or GWENs, placed around the site.
Like local network hubs?
Sort of, yeah.
Yeah?
They collect data not just from the vest, the cooling system status, the temperature, but potentially from other sources too.
Yeah.
Like local weather stations or even smartwatches the workers might be wearing.
Smartwatches. Tracking heart rate, maybe?
Exactly. So you can gather environmental data, system data, and biometric data all in one place.
Wow. So the cooling could become really personalized, adjusting based on the weather, how hard someone's working?
That's the vision. All this data gets standardized, semantically annotated, they call it, so different systems can understand it.
Mm-hmm.
Then it feeds into a central workplace safety controller.
Using AI?
Potentially, yes. Using AI to analyze all that data and determine the optimal cooling level for that specific worker. In those specific conditions, maybe even learning their preferences over time.
That's fascinating. But hang on, collecting biometric data like heart rate, that brings up privacy concerns, doesn't it?
Absolutely. And the researchers address this directly. It's a crucial point.
So how do they handle it?
Their proposed approach is quite interesting. They suggest building two separate AI models. One model links the worker's ID and the weather data to the cooling power setting.
Okay, no biometrics there.
Right. The second model links the biometric data, like heart rate, and the weather data to the cooling power. Crucially, the second model doesn't have the worker's specific ID attached.
Ah, so you break the direct link between the sensitive biometric data and the individual's identity.
Exactly. You can still use the relationship between exertion, indicated by heart rate, and conditions to inform cooling levels, but without storing or processing, John Doe's heart rate is X. They also mention using techniques like adding noise to the data or grouping data into buckets to further enhance privacy.
That sounds like a thoughtful way to approach it. Okay, so they built the vest, they thought about the system. How did they test if it actually worked?
They did lab tests. Controlled environment, 25 degrees Celsius, 65% humidity.
Okay, warm and humid.
6 volunteers wore the vest over protective gear and walked on a treadmill at 5 kilometers per hour. Pretty modern pace.
And what did they measure?
They measured local skin temperature right under the Thames and also in nearby spots on the skin that weren't directly cooled. They looked at the chest and the upper back, the shoulder blade area.
And they asked the volunteers how they felt too, subjective comfort.
Yep, they collected thermal comfort ratings at different points.
So what were the results? Did it make a difference?
It really did. They found a significant drop in skin temperature under the cooling modules. The biggest drop was on the back, almost 3 degrees Celsius lower.
Wow, nearly 3 degrees locally? That's substantial.
Definitely. And interestingly, even the skin next to the cooled areas showed a gradual temperature decrease over time.
So a bit of a wider cooling effect, not just a pinpoint.
Seems like it. On the chest, the cooled skin temperature stayed close to what's considered thermally neutral, which suggests the system was effectively preventing overheating in that area.
And the comfort ratings, what did the volunteers say?
Their ratings improved. They generally felt more comfortable shifting towards slightly cool or neutral, especially during the rest breaks they took between walking periods.
So objective data shows cooling, and subjective reports confirm people felt better. That sounds positive.
It does. It suggests the system works as intended to provide localized relief.
What about power? A cooling system needs energy. How long does the battery last?
They calculated the average power draw at about 7.55 watts. And using the 15 amp hour power bank in their setup, they estimated a battery life of around 7 hours and 21 minutes, roughly.
7.5 hours, near enough. That covers most of a standard workday, doesn't it?
It does. And they pointed out that the system probably wouldn't need to run at maximum cooling power constantly in a real-world scenario, which could stretch that battery life even further. They also mentioned this alternating operating mode the controller uses.
Oh, yeah. How does that work?
It runs at a higher cooling power for 60 seconds, then drops to a lower standby level for the next 60 seconds, and repeats.
Sort of pulsing the cooling, maybe to save power or prevent overcooling.
Likely a combination, yeah. It helps manage the energy consumption while still providing a noticeable cooling sensation.
They also mentioned safety regarding the TEM arrangement, right? Something about parallel versus series.
Yes, that was an important design consideration. They worried about the voltage level if TEMs were connected in series, especially considering potential contact with sweaty skin.
Because higher voltage could be a shock risk.
Potentially, yeah. They referenced a safety standard, IEC 604791, and determined a safe touch voltage level for those conditions below 7.1 volts DC.
Okay.
Connecting the TEMs in parallel, using a standard 5V power bank, kept the voltage well within that safe zone. A series connection might have needed a step-up converter, introducing higher voltages.
So the parallel setup was safer and simpler with the common 5V power source. Makes sense.
Exactly. Safety first, especially for wearable tech.
And this integration into the Assist IoT framework you mentioned earlier, what's the big picture benefit there?
Assist IoT is this big EU project trying to create standards so different IoT devices can actually talk to each other effectively.
Interoperability.
Right. So by designing this cooling vest to fit within that framework, it means it can more easily become part of a larger, integrated smart safety system on a construction site. The vest talks to the Gwens talk to the central controller, maybe other sensors chip in data too.
It creates a much more connected and potentially responsive safety net.
That's the goal, a smarter, data-driven approach to worker safety and well-being.
And the researchers seem serious about this. They mentioned a utility model application in Poland.
Yes, which suggests they see real, practical commercial potential for this design. It's not just a lab experiment.
Okay, let's try and wrap this up then. What's the main thing we should take away from this deep dive?
I think the core achievement is demonstrating that this kind of active thermoelectric cooling closing is genuinely feasible and effective. It significantly improves local comfort, which is a big deal for safety and productivity in the heat.
Yeah, and it's not just a standalone gadget. They've shown a clear path for how it could integrate into these larger, smarter IoT systems on work sites.
Right, with that potential for personalized, AI-driven cooling while still being mindful of crucial things like user privacy.
And for me, that nearly 3 degrees Celsius local temperature reduction, that really sticks out. It's not a trivial amount of cooling. It shows the real potential for this to become, maybe even standard gear in some really demanding jobs.
Absolutely. And thinking about you, the listener, where else could this go? We focused on construction, but think about firefighters, agricultural workers, miners, people working in foundries.
Even athletes training in hot climates, perhaps, or military applications.
Potentially, yeah. Anywhere that heat stress is a major factor, and where you need cooling without hindering movement. How could this kind of smart, personalized cooling change the future of work or even daily life in increasingly hot climates?
It's a really interesting question to ponder. It shows how technology is adapting, finding ways to protect us better in these challenging environments. It feels like real progress.
Definitely. And if you want all the technical specs, the detailed data, the original research paper is the place to go.
For sure. But it's a fascinating look at how innovation is tackling a very real, very hot problem.